Hello, thank you for viewing this presentation. My name is Sherwin Bagheri. I'm a professor at KTH in Stockholm. I'm going to present to you today is a work we have not yet published, but plan to submit soon. It's about Brinkman viscosity and how to determine viscosity from different type of scaling estimates. And this work has been performed mainly by Aidan Reinhardt, who was a previous PhD student in our group, and Ujis Latsis, which has been co-advising Aidan together with me. And the project has been financed by the Swedish Foundation for Strategic Research and the Wallenberg Foundation. So, right. So the whole background to this project is that we want to be able to efficiently model transport phenomena between free flows and porous materials. Right? That could be either advective transport, molecular transport of mass, energy, and momentum. And we want to do this with high precision. We want to also be able to do this without having to resolve every pore of the porous material. So there are different approaches to accomplishing this. One of them is the what we call the two-domain representation or effective representation. And one is based on a Darcy model. So you have your Navier-Stokes equations for the free flow above the porous material. And then you have the Darcy law in the porous material, which together with continuity gives some sort of a Laplace equation for pressure, as you can see there at the bottom right. And between Navier-Stokes and Darcy's law, you need to have some boundary conditions, which we call interface condition, which is shown here in red. So these interface conditions can be determined, and they basically consist at the leading order of a slip boundary condition for the tangential velocity components and a pressure jump condition for the pore pressure. And these boundary conditions, similarly as the permeability for the Darcy law, contain constitutive parameters, which is called here the slip length tensor L and the pressure jump vector B. And these can be determined from unit cell problems. So this is a well-posed problem that we can use. A different approach is to use the Brinkman model instead of a Darcy's law for the porous material. And again, you have Navier-Stokes in the free flow, but now you have, in addition to Darcy term for describing the porous material, you also have a second derivative or diffusion term for the velocity, for the pore velocity inside the porous material. As you can see there, it's a blue circled. It's mu b here is the Brinkman viscosity, which is introduced as a free parameter when you include this second order derivative for the velocity. So now again, you need to have some boundary conditions to couple the Brinkman model to Navier-Stokes, and usually it is a velocity continuity is used here. So UF equal UB, where UF is the velocity of the free flow and UB is the pore velocity. And then you also have another condition, which is the stress jump here. So sigma F is the stress of the free flow, and sigma B is the stress of the Brinkman model. And there is a R here is a jump coefficient, which can, if it's 1, there is a stress continuity. If it deviates from 1, you have a stress jump at the interface. So again, R, the stress ratio tensor is what we call R. And again, it can be determined similarly to in the previous slide, it can be determined from unit cell problems. However, what seems to be non-trivial to determine is the Brinkman viscosity mu B. So this is really the topic of this talk, is to how do we determine the Brinkman viscosity when we have a free flow over a porous material. And another thing that should be mentioned here is that classically a Brinkman model mathematically is perhaps not asymptotically consistent. It is actually, or it can be shown in some certain circumstances, is a higher order correction to the Darcy term. So this term is really relevant if you have very, very sparse inclusions in your porous material. Nevertheless, Darcy is used even for other solid ratios because of the simpler interface conditions which you have. So here you have velocity continuity, which is a major advantage numerically compared to having, for example, discontinuous velocity when it comes to implementation. So there are some sort of numerical advantages of using the Brinkman model compared to Darcy's law, which has also made it very popular. So it's a straightforward approach to modeling free flows of a porous material and has resulted in a number of applications using this model. For example, for turbulent flows of a porous material, tissue modeling, gels and polymer layers, and so on. So clearly it is being used, and it is a useful empirical, semi-empirical model, I would say. However, the issue remains of determining the appropriate Brinkman viscosity. And previous work, mathematical work in particular, have shown that, in certain limits, the Brinkman viscosity should equal the molecular fluid viscosity. So the ratio between the two should be 1. However, there are a number of works that have tried to validate this by numerical simulation, by poor resolved numerical simulation. And we can see that for different solid volume fractions, you can have a viscosity ratio between the Brinkman viscosity and the fluid viscosity, which is significantly different than 1. So here is a presentation of viscosity ratio as a function of the solid volume fraction for 5 different studies. 3 of them, which are colored here, are numerical studies. So these works have used Pore-scale, pore-resolved simulations, and validated the Brinkman boundary condition. And they have noticed that, well, as we can see from this plot, that viscosity ratio can definitely deviate from 1, especially for large solid volume fractions. There are also 2 theoretical works here by Okoa Tapi and Whittaker and Koplik et al. And these are shown here without symbols, so in purple and green. And we can see that they sort of get the opposite trends when it comes to high solid volume fraction, although they converge to 1 in very low solid volume fractions. So clearly, there's a sort of a question here: what should the Brinkman viscosity be, and how do we determine it in a practical way? Right. So this is the aim of this talk. So what we do is we take a very simple model problem where we have a porous bed. So it could, for example, is a 2D. So it could, for example, consist of these circles. And we drive the flow over this porous bed, either with a shear. So we have a plate at the top of this domain, which has a constant velocity, which creates a constant shear, and a linear velocity profile, which is shown here with blue arrows. Or we have a constant pressure gradient that drives the flow both in the free flow domain and inside the porous material, which is shown here with green arrows. So this is the problem we consider. And, the Brinkman model simplifies significantly for this simple system. So if we assume a very slow flow above the porous material, such that we can neglect inertia, we can consider a very small, thin domain with periodic boundary conditions, which you can see here to the far left on the slide. And it should be mentioned that we consider 7 different geometries, which are also shown here. So in addition to circles, we look at squares, triangles, or different orientations. In any case, regardless of the porous geometry, the Brinkman model simplifies and becomes 1D, as you can see to the top right. And you can solve this by hand. and that solution is shown at the bottom there. And what is circled here in blue are the three parameters that need to be determined to have a unique solution to the Brinkman model. So US here is the slip velocity at the interface. So the interface is a plane which we are placing on the crest of the porous material. And at that crest plane, you will have a slippage, a slip velocity. And that slip velocity can be determined basically for any geometry. And similarly, as permeability can be determined for any geometry. So Kxx is the interior permeability of the porous material, and that one can also be determined. So determining the blue ones is not a problem. We can do that. Now there's a pink circle here, delta. And delta contains, as this in the square root expression here, mu. And mu is the ratio between the Brinkman viscosity and the fluid viscosity. So that one, we don't know how to determine a priori, right? So this is the objective. So the objective here is first to do direct numerical simulations resolving the flow between the pores. So here we see that as we increase the solid volume ratio, we can see that the streamlines around these inclusions in the porous material change significantly. For very high solid volume ratios, we can see separation developing on the size of the cylinders. So having these direct numerical simulations, we can average them, volume average them, and then minimize the 2 norm by choosing delta in the Brinkman solution and determining mu that minimizes the error basically between the direct numerical simulations and a model using the Brinkman equation. And doing that, so we see that the best fit of the viscosity ratio is definitely not even converging to 1 for solid volume fractions, a very small solid volume fractions, as you can see to the left figure. And this is for all the geometries we considered. We can see they converge towards the same value, but that is not 1. And this is because we're not looking at the bulk porous material. We're looking at the inhomogeneous system where we have a free flow and a porous material, and we want to use the Brinkman to couple the 2 domains. Now, if we increase the solid volume fraction, we see that the viscosity ratio decreases first below 1, and then it very rapidly increases to become much higher than 1 for very large solid volume fractions. And as you see, this is again related to the topological change of the streamlines at the pore scale. So clearly, Brinkman is a very simple model. It's just exponential decay, and it cannot capture, for example, negative velocities that may exist inside the between the cylinders. In any case, we have investigated these 7 different type of geometries as are sketched here to the right: circles, squares, and rectangles of different shapes. And we can categorize these geometries into 2 types. So we can consider 4 of them as being rough and 3 of them as being smooth. So the rough ones are basically, if you can imagine that there exist stagnation points for the top layer of these porous materials. And there's a roughness effect induced by the top layer of these porous materials, in contrast to the smooth ones, which are basically porous materials that that the top layer is basically machined, so it's perfectly smooth. And we will see that this has consequences for modeling Brinkman if the porous material or the top layer of porous material is rough or smooth. Right. So what we did is now we have this data. We can see what the best fit is for the Brinkman viscosity. So the question then is, how do we determine the Brinkman viscosity without actually having to go through this process of doing pore-scale simulations, which of course we want to avoid. We want to use the Brinkman model without having to do direct numerical simulations resolving every scale. So what one can do is a simple scaling analysis. So let's take a look at the Brinkman viscosity in its most general form there to the left. And we can simplify this by removing the pressure gradient. So imagine just that you have a shear-driven flow, for example, and the pressure difference is 0 in the streamwise direction. So what you end up with in one dimension is the expression to the right. So you just have basically a u equals a coefficient multiplied by the second derivative of u with respect to y. Now we can introduce a characteristic velocity scale, uc, and a characteristic length scale for y, which is called L here. And then we can make the simple scaling estimate, as we can see in the expression in the center of the slide. And we can introduce as we can see, UC cancels on both sides of the expression, and we can introduce a coefficient C, which is constant and is order 1 actually, as we can show later. And then we can write that the viscosity ratio mu should equal a constant C multiplied by the ratio of the characteristic length scale squared divided by the characteristic permeability K. So I should have mentioned that K here, small k, is a characteristic permeability of the porous material, right? It could be the mean of the different components or whatever that is appropriate. So the question is then, what is the length scale, the characteristic length scale? So if we take now the category of geometries that we call rough, and then for these rough surfaces, we can define a length scale, which is the slip length scale. So if you have a Navier slip boundary condition, you assume a linear decay to 0 of your velocity profile at the interface. And the amount of distance that the velocity has to be decayed to reach 0 is called the slip length. And that is a characteristic, that is a length scale that you can uniquely define for any rough surface. And if we use that length scale in our expression, and that length scale we call LS, we get the expression to the top right. And we can also introduce some length scale for the permeability, which we call the pore length scale, for example. And we call that LP. So LP squared is some characteristic permeability. We get the expression to the right. So mu equals C LS squared over LP squared. And if we plot this expression now as a function of the permeability, of the interior permeability of the system normalized with the pore length scale squared, we can see that all of these different geometries fall on top of each other. So this scaling shows basically that the scaling is appropriate to collapse all the different geometries. However, the C coefficient is something we have to fit. So as you see, for different geometries, we have used different constants. However, the constants are all order 1. So they vary between 0.7 here and 1.2. Now, if we do the same exercise for the smooth type of geometries, we don't see the same collapse, right? And this points to the fact that the slip length, slip length LS is not the appropriate length scale in this approximation, in this estimate, right? So this scaling estimate holds for rough surfaces, not for smooth surfaces. So the question then is, can we use this scaling estimate to predict the Brinkman viscosity? Yes, we can. So here I'm showing you 2 plots. Let's focus on the left one first. So in both plots, I'm showing you E here. E here denotes the error between Pore-scale direct numerical simulations and using the Brinkman model. So in the left plot here, we have used Brinkman viscosity mu b by doing the best fit in the 2 norm to the average velocity obtained from direct numerical simulations. And we can see how the error varies for different geometries, which are rough here, as a function of the interior permeability. So we change the permeability of the porous material. And we can see the point here is that the error is around 0.3. So it's around 30% error you get by using the Brinkman model. So that's the best you can do with the Brinkman model. You cannot really get lower, at least in the 2 norm, than 30% error, right? It's just that the model has a limited capacity to represent the complex behavior at the interface. Now, if we, instead of fitting the Brinkman viscosity with the direct numerical simulations, we determine it through our scaling, and we put C equal to 1, right? So we cannot know what C is for every geometry, so we put C equal to 1, and then we get an error which is sort of which is shown here to the right plot. And what we can see here is that the error is not increasing by order of magnitude, is increasing by 10-20%. So instead of having 30% error, we have something like 40 or 50% of an error. And what we have, as you can see here, we have cut off the error. Actually, the plot is not showing the error above 0.4, and there are 2 vertical lines here which are in black in both plots, and those lines demark basically, if you're to the left on these lines, you are doing basically porous materials which are not realistic to have. So basically, we are interested in looking to the right of these vertical lines, and there we can see that the error to the right, in the right figure, is around 0.35, and to the left is around 0.30. So using this scaling estimate is a good proxy of the best Brinkman viscosity that you can get by fitting the 2 norm. Right, so I want to conclude by mentioning what we have basically presented here. So the Brinkman model, I think, is an empirical model. It's not rigorous, it's an empirical model that you can use with a reasonable accuracy in applications, which I think could be interesting and a good model because of its simplicity, and because of that it conforms mathematically better with the Navier-Stokes equations than what the Darcy model does. Now, the question, of course, is what do you use for the Brinkman viscosity? If you don't want to be mathematically rigorous, the Brinkman viscosity is really just a fitting parameter. And how do you choose it? And we have shown here that you can actually, for certain type of porous materials which are rough, you can use a simple scaling estimate to having the slip velocity and having the internal permeability, and both of these quantities you can compute a priori. Then you can predict the Brinkman viscosity. Now, how do you know if the surface is actually rough or smooth? Well, there is a way of doing that quantitatively. We have defined a quantitative way of determining or distinguishing between rough and smooth surfaces. I did not show this in this presentation, but we will have this, show this in our preprint that should come out on arXiv soon. Another thing that we didn't discuss so much here is error estimates of the Brinkman model. And we will, there's more to say there, and haven't talked about that either. Finally, you can do the same exercises here for random and irregular porous media. And in fact, it turns out that the scaling estimate holds also for this type of porous materials, and the errors are much smaller. So this is good news if you want to use more natural type of porous materials which are not perfectly structured. Right. So again, I want to huge thanks to Ujis and Aidan for performing the work, and this is really also their idea. I just had the pleasure to present it to you. And if you want to know more about our work when it comes to porous materials, you want to reach out to us, please visit our homepage. And the preprint of this work should appear in a month or two, also on this homepage. Thank you very much for listening. And reach out to me again if you have any questions.